Well, welcome everybody to HydroTerra's latest webinar. Thanks so much for everyone turning up today. Today we're talking about harmful algal blooms, a global crisis, how AquaWatch Australia is advancing measurement, monitoring and early warning systems. Our presenters, we've got two presenters today. We've got Tim Malthus, who's Senior Principal Research Scientist at CSIRO, and we've got Nguyen, who's hydrodynamic modeller with CSIRO. Before we get started, I would like to begin by acknowledging that we conduct our work across this great land, and for that privilege we would like to thank the traditional owners. HydroTerra respectfully acknowledges the Boonwurrung people of the Kulin Nation, where we are located today, and we pay our respects to their elders, past and present. There's pictures of our presenters. Both look a little bit younger there. A little bit about our two presenters. So, Tim Malthus. Tim is a Senior Principal Research Scientist in the Environment Business Unit with over 30 years experience in remote sensing of water quality with a focus on optics, calibration and validation, field spectroscopy and sensor development. Tim is a co-creator of CSIRO's patented Hydrospectra, near-surface sensor for the measurement of water quality parameters. As part of the AquaWatch Australia mission, he leads the in situ sensor networks work package, working with optical and electronic engineers and scientists overseeing the challenge of development and deployment of sensor networks at wide spatial scales. Dwi is a computational modeller with expertise in fluid dynamics and turbulence modelling, particularly in rivers, lakes, estuaries and air-sea interactions. His research spans stratified flows, turbulence processes, physical oceanography and marine atmospheric boundary layers. More recently, his work has focused on water quality modelling to support management of inland waters and provide early warnings of harmful events, including fish kills, blackwater algal blooms and sediment transport, using a combination of process-based and data-driven approaches. Dwi leads the development of AquaWatch Australia's inland water quality monitoring and forecasting products, aiming to deliver operational and actionable insights for water managers. His goal is to provide effective science-informed solutions to address pressing water security challenges in Australia and beyond. I think it's fantastic that we have CSIRO working in this area, and really lucky to have two people who are specialising in algae management, and it's great to see Australia leading in this area. Next slide. Sorry. Why is it moving? Before we get into the presentation, we love your questions. If you'd like to raise a question, please use the Q&A button at the top of your screen, and I will read your questions out at the end, and hopefully Tim and Dwi can answer them. Why does HydroTerra do webinars? Well, we like to share knowledge, we like to facilitate education, we like to take an industry leadership position, and really enjoy learning a lot from these people. So without further ado, I'd like to hand over to you, Tim.
Great. Thank you very much, Richard, and good morning, good afternoon, everybody. We are welcome to this webinar, and it's a great pleasure for myself and Dwi to be presenting this on behalf of AquaWatch. We gave a presentation through this webinar series back in April 2024, so it's a very useful opportunity for us to provide you with an update on some of the work or some of the progress that AquaWatch has made since that presentation presented earlier. And in this seminar, we're just very keen to update you on where we've got to on some of our inland water work, particularly around the monitoring of algal blooms and particularly the prediction. I am very much the warm-up act here, leading up to Dwee's presentation towards the end. So I'll just try and set some context, talk about AquaWatch in general, talk about a hydrospectra sensor, which is a data set that Dwee uses, and then hand over to him to round the presentation off. So if we go to the next slide, thanks. I just thought I'd set some more global context of algal blooms in inland waters. The sort of key conclusions here are taken from some very recent key articles summarizing the status of algal blooms globally. Those are down the bottom. I should point out that I should add that there was a very good review led by Anasuya Willis, but with lots of from CSIRO, but with lots of other contributors from universities and the like, on algal blooms, also undertaken under the auspices of Water RA, which was a very good capture of the state of the art that was released just earlier this year. But the context is that algal blooms are increasing globally, affecting a significant number of lakes worldwide. We're all aware of the key drivers, notably nutrient enrichment, but we also have this exacerbating effect of climate change, I guess, and global warming, increasing lake temperatures, perhaps increasing the durations of lake stratification, so that we find that algal blooms are both increasing in frequency, might have earlier onset times and longer persistences as well, as a result of some of those warming effects. Nearly always caused by cyanobacteria. Of course, there are blooms by other species, but if we're talking about harmful, I guess, in this context, most of them, I guess, are largely the different species of cyanobacteria. We're all too familiar, and these images all come from the Murray-Darling Basin on the left of the slide. We're all very familiar with the ecosystem impacts these things can have, oxygen depletion, fish kills, et cetera. And increasingly, of course, as those effects are getting more widespread globally, then the economic impacts, both from just the magnitude of dealing with these issues, but also the risks of societal impact through health and things like that is also high and increasing as well. Next slide. Thanks, Richard. If we then move to thinking about monitoring, if the problem is getting worse, then our current systems of monitoring, which are already perhaps declining with lack of investment, the challenges become greater and very much globally. Drawn from those sources of literature before, we have very limited and uneven coverage. So there's a spatial temporal bias. There's lots of work done in the Northern Hemisphere, a lot less done in the Southern Hemisphere, for example. A lot of that is focused on larger water bodies, I guess more important water bodies. There's a real breadth in methods and standards of data, methods of collection across different countries and states, and a few global data sets. Always the challenges and cost, I guess, of detection identification, particularly around using microscopical methods, taxonomy. The episodic nature of the bloom events is always a challenge, and that key challenge is detecting, what strains might actually be, or what parts of a bloom might be toxic versus non-toxic. Where the capacities for toxin measurement are increasing, but of course they don't encapsulate all of the toxins, the whole variety of toxins that might be present. They do have detection limits as well. Remote sensing is a key tool, as we'll talk about here, for monitoring across large areas, but this itself comes with its own limitations, which I've listed a few of things there. There's limited early warning capabilities, institutional barriers. Certainly, we're finding in AquaWatch, a key roadblock is just simply the availability of data and the way it's stored across different jurisdictions. I'll leave it at that. Next slide. Thanks, Richard. I've worked on that a lot. You'll see that I've chosen the color of my shirt to match that top right image, which is taken from Lake Burley Griffin by a CSIRO colleague of ours. The structure of the talk is really for me just to introduce AquaWatch, kind of some illustration of where we've got to show an illustration of our web products portal, which is still under development, but we're making great progress. I talk about the hydrospectrum instrument, and then I'll hand over to Dwi to finish off the presentation on forecasting systems. Next slide, thanks, Richard. So AquaWatch, if you recall, if you were present at the earlier seminar we gave, and maybe you're familiar with it anyway, but the concept of AquaWatch is a kind of ground sensor to space sensor network of observation systems monitoring, let's say continental scale water quality issues, and the integration of those data sets through a data center, through a data. Let's call it a data center, that box that is called AquaWatch data system. So we're kind of satellite sensor agnostic in a way. So what we're looking to do is accumulate data from Earth observation sets, sensors, irrespective of what sensors they are in a way, and this way we can make a sort of virtual constellation of sensors, take advantage and increase the temporal capability of observations. So in situ sensing, as I said, is a key component, and we'll get on to that. And the whole idea is this ground to space-based integration. So using ground observations to overcome the limitations in satellite observations, but at the same time, the satellite observations provide that spatial context we can't always address in the ground-based systems. The capability of AquaWatch we're providing through the data center the data integration system, a key system where we can integrate this data and particularly bring in modeling and artificial intelligence. Next slide. Thanks, Richard. So there are a number of key tools that we're delivering as part of this, and they're just sort of summarized in textual form here. I think in this presentation, we'll really touch on the top four components: water quality sensing, Earth observation data. Dwi will give a nice demonstration of how we put this all together in the data systems and modeling on the right-hand side. A lot of our work has been working with end users in co-design and through pilot sites, and I'll talk very briefly about that on one slide. And a lot of this is driven by a process we've called the Science and Applications Traceability Matrix, which is a system of converting essentially end user needs into actual stated measurement goals for certain parameters that we need to see in our sensors and Earth observation systems or in our water quality products. Thanks, Richard. So as I indicated, the real backbone behind AquaWatch is what we call the Easy AquaWatch system, this data integration system. And this is based on open data cube technologies, which are a very clever way of storing and processing satellite observations, given that those are really rich, really high volume data sets. This is we have a system that allows us to store satellite data in essentially analysis-ready form, and a system that then organizes that data that makes it much simpler to inquire and process that data to realize things like time series of products for individual water bodies or spatial products to look at the state of a problem over wide areas. So we have the system then that it's integrating in situ sensor observations, satellite observations, and then integrating it with ecosystem models, and then the magic happens in the middle, where we can then do that analytics and forecasting and provide certain delivery services out of the right-hand side of this diagram. Thanks.
Just before we move on, so the ecosystem models. So that's some model based on the actual real life physical situation.
Yeah.
So it's a bit like your conceptual model.
Yes. Yeah. So So Dewey will demonstrate that in his part of the talk, where we're taking very much a sort of lake ecosystem models, that are both taking in the hydrodynamics and the biology of certainly the pelagic system, and in trying to make a forecast on the basis of that.
Okay. Next slide.
Next slide. Yeah, thanks, Richard. So I'll just show very briefly just some illustrations of the AquaWatch web products portal. If you go to the next slide, thanks, Richard. So this is just a sort of slice of what we've been doing in the inland water space. We've also been doing a significant amount of work in the coastal water space, but I'm not showing any of that here. This is just an illustration, and this is very much a work in progress of our application notably of Sentinel-2 and Landsat data towards the derivation of a number of products for Australian inland water bodies, both reservoirs, lakes, and rivers. In three particular areas, we've developed the chlorophyll index, and I'll show some zoom ins in a minute of these. One for estimation of total suspended matter, and we've also been using Landsat data to estimate the skin surface temperature of lakes, at that important parameter, of course, in what might be driving algal bloom growth. I think, if you skip to the next slide, Richard. So just zooming in on a portion of New South Wales and Victoria, just to show this in a little more detail. This is a chlorophyll index based on the publication there, and the utility of this kind of approach is that so blue means not a lot to worry about. Red means we've really got something cooking in a particular lake that might require investigation. But this shows the power of the system, where we can get an overview of perhaps at a statewide level what is kicking off where, and that might require some investigation. So if we start looking at those amber and red dots on this map, they might perhaps warrant a investigation by a field team. I said at the moment this is a chlorophyll index. So it's not actually quantified for chlorophyll itself, but it's currently under the process of validation, and we'll be releasing the chlorophyll product quite shortly. Thanks, Richard. The next slide just shows the same for the total suspended matter. Again, so this is in milligrams per liter, and you can see that quite nicely at certain observation points down in the Murray-Darling system, we get quite a number of hits. This is Sentinel-2, and so sort of 10-20 meter resolution data plus, well, Sentinel-2 data on its own. Sorry, I don't believe Landsat data is used in this process. But you get a good overview of where those high sediment issues might be arising, and again, this work is based on a previous publication from CSIRO and Geoscience Australia. We're very confident in the algorithm. Perhaps it needs a more widespread validation, I'm sure, and that is underway as part of this process. And the final slide, Richard, is in the same, just to show temperature products. And again, I'm not sure what you conclude from this. If we were to look at the wide scale variation north to south across this north to south, we'd see very much of a gradient in temperature. The key benefit of these tools, which I'm not showing, is that we can sort of double click on any of these water bodies and then look at a time series over time and begin to understand, dating back to when Sentinel-2 launched back in the mid 2010s, you can then begin to look at lake behavior in terms of its temperature changes, its suspended sediment changes, and its algal bloom behavior as well. Thanks, Richard. Let's move on.
Is that suspended sedimenting more a measure of turbidity, or is it actually able to? Right.
Yeah. So a lot of our time series products show suspended sediment significantly increases around flood events, perhaps post bushfire events as well. thanks. I'll move on now to talk about hydrospectra. A brief introduction to this. Yeah. So just as an illustration of those sort of co-design with collaborators that I was talking about before. This is a number of pilot projects we've been working on both here in Australia and around the world, both in coastal and inland environments. Just kind of to illustrate that we've been, as part of the AquaWatch experience, developing a lot of experience in deploying in situ sensors, learning a lot in the whole process, and deploying sensors in a whole range of different environments for a whole range of applications. One of those instruments we've been deploying is the thing that you can see occasionally sticking out from buoys, like the one on the bottom left, is the hydrospectra sensor, which uses spectral reflectance. If you go to the next slide, and this is perhaps a useful slide just to ground us in the use of Earth observation and other sensors for monitoring water quality, is that if we look at spectral reflectance, like the graph on the right at high spectral resolution, and changes in that spectral reflectance as chlorophyll concentrations in water bodies rises, we see very much a change in shape, where the shape of that reflectance is very much punctuated by absorption features due to pigments present in those phytoplankton that might be causing a bloom. So we can see distinctive signatures of chlorophyll A, and then another one, a smaller feature that indicates the presence of blue-green algae, the phycocyanin feature, at around 620 nanometers. The two arrows indicate that if you see a small peak to the right of that chlorophyll A absorption dip, and if you take a ratio of those two wavelengths, you get a very strong correlation of chlorophyll A concentrations, and that's the basis of the tools that we're developing, and certainly the basis of that satellite-based tool that I showed you earlier. Thanks, Richard. So to take advantage of that spectral reflectance signature, we have developed in CSIRO this hydrospectra instrument, which you can see on the right, which essentially has a number of optical inputs that allows us to collect the data that we need, or the measurement we need, at a number of different angles, and of the sky and incoming radiation, as well as water reflectance, in order to accurately estimate the reflectance of the water itself. And there are some much larger, much more expensive scientific instruments that have been deployed for calibration and validation of ocean color observations. That small little inset on the left of the instrument you can see is one such system that we have deployed at Lucinda Jetty, but very expensive system. The whole idea of this device was to try and mimic those sets of measurements that instrument is making, and do so at a much lower cost point, such that we could make more of these devices and have them more spread out over areas, and be monitoring algal blooms at a high temporal resolution. So this device monitors the spectrum, just like we saw in the previous slide, at 15-minute intervals from sunrise to sunset. It includes all the sort of facilities for actually transmitting the data it collects. Has a number of other gizmos in it. It has a couple of cameras in it, which are really useful. One for photographing sky conditions, and one for looking at the conditions in the water itself. And it's the data from this instrument which Dewey is using at this very high temporal resolution, which Dewey is using in his models. Next slide, thanks, Richard. So we have a data processing chain which takes the raw data out of these images. It has quite a unique way in measuring these spectral inputs and then calculating reflectance, which I won't go into, but you can also see some examples of measurements of images taken from the camera. But we have a processing chain which allows us to then convert those raw inputs into reflectance data, and apply some quality QA/QC approaches using what's called the QIP, a QIP score, which is a very useful tool for allowing us to determine how good a particular spectrum is. And then you can see some illustrations of two two data sets of two reflectances taken over time on single days, one taken under very clear sky conditions, which is the spectra very close together. The other one's on the left, taken under more cloudy conditions. And here we see there's a bit more variation under clouds, quite understandably. But we have some good tools now to QA/QC these data sets. Thanks, Richard. The next is just a comparison of, if you just push the button one more time. Thanks, Richard. Yeah. So this is, we put one of our hydrospectra instruments beside that very expensive device at Lucinda Jetty in the Great Barrier Reef, and did a comparison of the spectra that we can obtain from hydrospectra. And you can see the two compared on the left-hand side, and there's a scatter plot of different wavelengths on the bottom right. And so we're quite happy that spectral shape-wise, this device, the hydrospectra measures spectral reflectance above orders at high spectral resolution very well compared to this more expensive device. Thanks, Richard. And so I just thought I'd illustrate this from the point of view of algal blooms. This is a nice study. We've had a number of these devices deployed at the Melbourne water treatment ponds in work with Melbourne Water. This just shows a series over about a sort of 7-day period of very high dynamic algal behavior in some of those ponds, very, very rich in nutrients, a lot of algal bloom dynamics. And here you see very much this change in behavior as the algae, as you can see from the video, are appearing at the surface and then dispersed through wind action or sinking through the water column as well. We can pick up the features of that dynamic behavior very much in the spectra that the hydrospectra measures. And if you, one more click, Richard, should show a whole range of spectral reflectances at the top of the graph. And so you can see that when concentrations are very low, or the algae might be lying deeper in the water column, we don't see much of a signal. But then as that surface expression in particular becomes very clear, we see that very distinctive algal response, algal signature. And I'll leave it there, Richard. I think I'll move on to give Dwee some more time. So just sort of summarizing all of that in a single slide, we use this concept of the spectral signature through hydrospectra, a cheap way of measuring reflectance to determine spectral signatures, and we can convert that information through that ratio of wavelengths I showed you. And the scatter plot shows the relationship for a number of Australian water bodies there. The graph in the middle at the bottom is simply a comparison of a time sequence of algal blooms taken in a prawn farm, another water body where chlorophyll concentrations vary very widely. And this is just a comparison between what's being measured by hydrospectra versus what's been measured by a exosonde fluorescence meter, and you can see the two correlate very well. So without further ado, so what we have here is a very rich data set, very high temporal resolution, lots of spectral information, and this is the key. We can see that we can accurately convert this information to chlorophyll data, particularly in high algal bloom conditions. And this is the data set that Dwee has been using in his modeling. So without any further ado, I'll swing over to you, Dwee, to go through your slides.
All right. Thank you, team, and thank you, Richard, for organizing this seminar. And thank a lot, everyone, for tuning in. And as you already see, team, talking through how you use satellite and then hydrospectra to monitoring some part of the water quality parameter. Now I will delve into a more technical part of how we build up a modeling. So today I talk about how first it's about how we use a process-based model for cyanobacteria bloom, and of course in a combination with hyperspectral remote sensing. This is go through some of the way how we do it. I will show some result and a limitation, and how we overcome the limitation by using machine learning. Next slide, please. Yeah, and then the work fit into the whole AquaWatch concept where you have all the in situ graph sampling or satellite or higher spectral data will fit into the model to provide the early warning and forecast. And of course, it going through our AquaWatch data integration and analytics system. Next slide, please. And one of the reasons why we address it is because processes in aquatic system normally run across many time scales. So you may have the hydrology event could range from seasonal to weekly, and then feeding into meteorology, which scale may be daily. And you have some certain algal physiology which happen within hour, or some of overtuning of hydrodynamic or breakout stratification would happen in the matter of minutes. And then the characteristic of our modeling and monitoring and modeling it also by on spatial resolution, where you may do for inland, you may have multi-purpose reservoir with the order of 10 kilometer resolution, down to an urban lake of kilometer, or water treatment lagoons down to 100 meter, and for example, you also have a river down to around in the order of 10 meter. So to deal with the different of temporal and spatial resolution like it, you need a different way of monitoring. So you need to have something that sufficient enough to resolve the small scale problem, but you also want to scale up with broader scale using, so that's why we try to address that using both from ground to space, both satellite and in situ sensor. And so the next slide, please. So JIT1 is showing one of our local monitoring system that we have. You can see that there's the hyperspectral camera, the one that Tim talked earlier, where it recorded hyperspectral image every 15 minutes. And it remotely IoT sending the signal to our data analytics system. You also have a meteorological station where you record the meteorology data for every 15 minutes. The thermometer chain to record a vertical temperature profiles with every 10 minutes. We also do water sampling, whether it also depends on our partner, but normally we hope to aim it with a bi-weekly water sampling. Yep. And of course, all of those need to drive by a set of governing equations. This slide not trying to scare you away. It is more like to show you the process that we're dealing on the process-based model. So for example, here we have physical processes where you're dealing with the mixing processes driven by wind or driven by the temperature, with feeding from the long wave or short wave radiation. You also are dealing with temperature gradient and heat exchange. And all of it is defined here by a covered K epsilon turbulent model. And though it will get into the output, will get into the input of a biological competition processes in a lake. Here we simplify it, where the population of a phytoplankton, it depends on light and temperature only, where you have a specific growth rate and growth loss function and life field, or it's a function of light and temperature. Next slide, please. And so that two model will fit into a process change, where you have the external forcing it, the meteorology, or whether you also start your initial condition with temperature, flow condition, or cell count. So the hydrodynamic, one note is that it is all 1D modeling. So the hydrodynamic will split out the temperature stratification or temperature profile and the mixing. We fit in that into the grow model, and then it run out, driven by our metrology. Also, it restart by the cell count convert from the high-res spectra data. And then it's split out for you the cell count in 1D 1D profile. And you can see that JIT1 is taking advantage of the weather metrology, where you have you could use the forecasted weather to actually forecast the output of the process-based model. And the next slide, I will so this slide show you some of the results. The first thing is the temperature stratification. So this one showing that we testing using our model running whether you use an in situ weather station or a meteorological service station, and we compare that with our simulated weather data and also the thermometer chain, compared it with the thermometer chain. You can see that because it's 1D, so for it's the time series, it basically capture the trend of the stratification event and the temperature structure. However, it surely that cannot capture the horizontal, for example, an increased flow of horizontal processes where you have a cold inflow in there. So surely JIT have some advantages because it light, it run very quick, but it also have disadvantages. Next one, please. And for sure that one flexibility of our model is you could test it out with different species with different parameters. For example, here we could change the optimum growth temperature for 32 degrees for Chrysosporum or 28 degrees for Microcystis. And then it could actually beautifully leave out to you a time series of profiles of how the condensation look like in the water body. The next slide. JIT-BG slide is showing you how the model perform with the top panel where you see the black solid light. It is the simulation. All the blue and black scatter dot is the high-res spectra, so it's the conversion from the high-res spectra. And then all the colorful dot down there, circle and triangle there, is the sampling. And you can see that, of course, there is a mismatch between of those data sets. However, if we zoom in and then, for example, the down panel where you zoom in at the February of 2020, and you can see that it actually captured well in the plate of the bloom formation. So one advantage is of JIT, it like say that it's good to monitor the trend and the bloom. It's not good for capturing a very fine detail of concentration of algae in the water. Next slide, please. And another result here, JIT1 showing how we change the changing of water level will change the stratification and cyanobacteria distribution at the dam. And JIT is relatively important because, for example, the example of the dam here, it had two outlets, a hydropower and irrigation outlet. So people, the dam operation would like to know what is the better option for whether they open the dam and release the water in, whether it's seeding the cyanobacteria downstream. And I also want to note that our model could deliver the result in a matter of minutes, so it is real time. So it's really good for an application of dam operation, especially in an example here in this case. Next slide, please.
Just before we do, Dwee, so the headings bathymetry, is this able to actually look at the depth of water
Yes.
as well. So it can over time see a change in the form of a channel or the form of a lake bed, or
No, I mean, bathymetry is one of the input of the model. What I mean here is that if you know the chain of the bathymetry, you could put that as an input to see how the chain of that bathymetry will change in the cyanobacteria concentration.
oh, I see.
Yeah.
No problem.
Yeah, and last but not least, our process by forecast. So it's short term, because it's based on the weather forecast, and it's driven by actual meteorology. Here is one example where you see that the index pattern is well described, where when we run all the color light, when we run the forecast every day, you can see that it match pretty good with the baseline as well as the higher spectra. Next slide. And of course, our process way and 1D, it surely had uncertainties. And one uncertainty is that we, in the bottom panel there, the photo just showing there is the chain of dominant species. It's changing over season or annually. And that it means that you cannot make a long-term simulation. And then we also cannot overcome summer problem when it's slipping over the winter time. It's only that because of the short time forecast, it means that we also need to know the mixing state, and that is normally like in our data sets. And it is also a homogeneous first order DPE equation in time. It means that it also have some of the disadvantages on that. And the next one is in the right hand side, where you see that it also different of the bio volume and the number of cell count. Because of the size different of the species, you can see that sometimes you have a large bio volume, but it's not necessarily a large number of cell count. And one limitation that we are not actually addressing the potential of the toxicity concentration here. So it means we need to actually focus on a potential toxin producing species, and just run and focusing on that species alone. So that is also a limitation. The next slide, please.
Is that difficult to do? Like, it sounds difficult to be able to separate between these species using this satellite data, etc.
Yeah, so one of the research development process of the step that we are trying to do in AquaWatch is trying to build a spectral library and couple that with a toxicity library. And that part that if we could collect both of them, then in that case, then if we would easier to identify the species and the toxin and do the matching things better. But for now, JIT model is not addressing that. Yep.
They look pretty similar, don't they? They look pretty similar to the human eye.
Yeah, JIT one just show you that another limitation is because we use the cell count driven by the high spectral camera. It means that we try to derive that through the thing that you see in the surface, and you can see in the figure here that what actually in the water column. It normally sometimes it's not actually necessary what you see or derive from the surface. And one thing that because if you want to deal with a buoyant species, then one thing you want to know is whether what is the mixing, how is that mixing carried out or mix the buoyant species in the water column. And this is normally difficult because you need to know the internal mixing dynamic and you need to fit that in the model. So an assimilation of high frequency data from the hyperspectral reflectance will have improved it, but I will show later on show you also another way we use AI to improve this problem. Next slide, please. Yeah, so yeah, uncertainty for sure for our 1D forecast harmful algae bloom using a process-based model. First, because it 1D, it uncertainty in a lateral distribution and transport, and the meteorological driver it get a change in simulation based on the weather forecast. Sure, and you don't know the mixing dynamic, and of course the species composition, dominant species, toxicity, and then you also forecast by cyanobacteria on the hyperspectral data, only driven on the surface. So that it lead to another uncertainty. So how the AI or data-driven model would have. So the first thing first is the next slide is we try to improve our process of pre-processing. So one thing we want to do it first, we want to filling the data or inputted the data, and one trial we do here is we use the foundation model. We try to use that with the Lower Murray River, and for a certain number of water quality parameter. It is noted that it one is submitted to IEEE via SL journal. It's not been published yet. And want to show the next slide at the results, how it look like. So JIT one, you can see that we tried out with 3 parameters. So turbidity, chlorophyll, and TSS. You can see that it doing pretty good in cloud affected data, where we show the gap fill. Note that it one is not the filling in temporal, but also spatial spatial correction as well. So you could see the gap fill and how it perform in here. Yeah, so that is the first step we do. We try to improve our pre-processing of our data sets. The next one, please. The next one, it also show how the AI could help. So one part that I said earlier, that we actually have unlimited knowledge of the mixing state in the water body. How could AI actually help to predict the mixing state? And here we use the machine learning model, and so a case study of Menindi, where you have your data source to train. It actually coming from public data source, whether it come from Bureau of Meteorology, Water New South Wales, or some of the commercial meteorological company. And though kind of parameter you can see here, for example, radiation, evaporation, minimum or maximum air temperature, water level, humidity, and all kind of things that it actually provides by the public government company or a commercial company. And then you gather them all together, putting them as a feature inside your machine learning model. You couple that with a hybrid model, and then turn out to do the prediction of mixing or non-mixing. The next slide, we also showing that we also using an explainability to actually predict of what kind of parameter will affect your prediction the most. And at the result in here, we use the survey explainability method. Then the minimum air temperature, it had the most affected for the mixing processes. And also we also found out that if you couple with machine learning, support vector machine learning, and the hydrodynamic like 1D model, it gives you the higher F1 score. So the higher F1 score, it means that the better prediction of the model is. So basically, I just want to say that using a hybrid modeling in here give a better prediction for mixing and non-mixing. And the kind of knowledge that actually you want to fit into the back into the process by model that I saw earlier to improve one of the limitation. We want to overcome that. The next slide, please.
Just before we do, Dwee,
Yes.
so just so I can make sure I've got my head around this. So on the left there, we've got this conceptual model of mixing, and then you create a numerical model of that, which you're calling the hydrodynamic model. And then you're coupling that with this machine learning or AI somehow to come up with the best fit against your observed results. Is that right?
Yes. And there is a quantity that provide you whether a water body is mixed or not mixed. For example, we have the Smith index or accuracy, all of those kind of stability parameter that helping here for you to predict mixing or non mixing. Then when we set the trial on all of that kind of thing, then when the model put out, it would tell you whether the water is mixed or not mixed. So all of the physical part in here, it actually, we call it a feature. It's like parameter you put into your classification algorithm in the machine learning. And then you run that combined with hydrodynamic.
So when you're looking at the amount of, I guess, primary monitoring data you've got to actually calibrate this against, do you have like the amount of time series data, etc., you need? How do you determine when you've got enough to allow the machine learning to actually do its job properly, as distinct from sort of making it up?
So of course, surely that you also need to have a certain statistical comparison at the end. Whether, for example, you could have a mean square root, root mean square root, or a correlation with the data. And you really don't know, you really don't know that how much data it. Of course, the more the merrier, but surely that, for example, one of the part that we figured out is we also try to optimize not just how many computer resource you need, how long that you need to run it, and how many data that you have. And then it is some certain kind of study that we also need to done as well. We actually did that. If you go to the next slide, then we actually did that with JIT1. So JIT1 is the hyperparameter tuning. And before delve into that, we say that, for example, the 64 million combination, when we try to hyper tune it, we figured out that it's better for us to have around 300 point of data set. It more like we try to train that with like less than 100 point, 200 point, and 300 point, and then we figured out which type of the best for all that optimization. So to answer the question, then it actually need a study need to be done to see that how much data that you need for each of the model that you want to train. Okay, so this slide is showing you that how we overcome with the manual link calibration process. And one thing we do is we use the hyperparameter tuning method, where you have the machine actually hypertune, compare between your model output and the in situ data, and then give it out for you. It just scanning through everything and give out to you the best output with, for example, the best coloration with your in situ data. And then JIT particularly good for me when I actually trying to tune manually with 12 parameter or 9 parameter of that two model before. And then it take a lot of time, trial and errors, and sometimes you are not nowhere near the optima. JIT1 you let machine to do that for you. Another thing is for the high-res spectra you see before, you want to how to do the conversion from that high-res spectra data to chlorophyll. One thing you can do is you set the combination of band wavelength and then set the fitting with your in situ data. Your kind of thing, if you do manually, like I see here, when you have 3 different band and then going through the whole set up all the hyperspectral wavelength, then it normally that come in here, for example, 64 million combination with a lot of fitting. Then here the machine that running and then do that to picking you the type bed algorithm for you. We also trying something it called genetic programming, where you don't even need to set the type equation you want to looking for. You just only set the type mathematical rule and then set that, and then it split out the equation for you. One limitation of this is for sure that if sometimes you cannot explain the equation that is split out, but that's why you still need an expert for annotation here. However, I say that it surely that have to reduce a lot of manual laboring process of doing manual calibration or a manual tuning for estimating the chlorophyll. And you can see that all of it fit nicely in the last part. It when we have the data out, we fit that in our AquaWatch web service and dashboard. So that's why I want to come up with the next slide when I show an example of the dashboard. So you can see here is an example of dashboard that we provide to our client, where you see when they have the chlorophyll, they click in, you have chlorophyll monitoring. You also have temperature stratification. It's important that one important thing is it not just provide time series of the historical data, but it also provide the forecasting as well. I also want to showing an example of one thing still on research and development state in AquaWatch from our research engineer, Stitham, his email there, where he actually tried to training a LLM model with a lot of database, research from literature report, like, and then coming up with a co-pilot where the client could actually click in here and then ask the AI how the data and how the result it makes sense and what is the action for them for management purposes. This is of course really still in a development phase, but it's something really exciting if we could go to this part at the end. Yep, and this is my last slide. So I say that doing modeling, it's not just only doing process-based, we also using AI, and we call that a knowledge-guided machine learning. So you may, if you work on modeling part, you may heard of something it called physics-informed neural network. That is something where you use physics to guide your machine learning. Here we not just only use physics, we use physics, chemistry, and all of the operation knowledge to actually train our machine learning model. And some example here for water temperature, dissociation, stratification, and chlorophyll. Yeah, so I think it is some part that I want to end up with. We got hybrid modeling, maybe it's the future.
Certainly looks like it. I think maybe a lot of numerical modelers would be keen to get better around that.
Yeah, one slide before you can see that I saw that the F1 score, if you remember, it means that we will say that compare between only data driven, only physical by, or some certain set of combination. So we saying that doing it hybridly give the higher F1 score a better prediction. So that, yep, one thing. Now I hand over to Tim for the conclusion.
Yeah, thanks very much, Dwi. A lot to take in on that modeling stuff. Sorry, Richard, could you go back to the previous slide and just run through the conclusions? Yeah, so yeah, it's been 18 months, I think, since we sort of last updated you where we've got to in AquaWatch through this forum. And I hope you can see that we've made some considerable progress in developing the underlying tools in AquaWatch. And I think this whole idea of an integrated sensor satellite monitoring and forecasting system, yeah, really provides a very unique approach that we're working on. And it's all designed, of course, particularly in the inland water space, to provide comprehensive and reliable water quality services across Australia, and also that allows us then to manage those water bodies better. And I hope through this presentation you've seen the novelty and some of the approaches we've taken in the development of sensor technologies, and also as what Dwi has outlined and has coupled hydrospectra, deterministic and hybrid modelling systems, leading to quite realistic approaches. So these are all very much works in progress, as I indicated below here. But it's very, very exciting. I think we've made considerable progress. I should point out that the title did refer to harmful algae, and of course there's a lot of nuance around what determines harmful. We of course haven't talked about that next step, which is that determining, you know, what algal bloom might actually be harmful, as in harmful to perhaps animal species such as other animals and humans. Of course, I would regard all as being harmful at high concentration for the environment. So that, you know, that's one thing we haven't talked about, but there are lots of other people doing work in the toxin space and the genomic space as well. So thanks very much for listening. We'd be very happy to hear from you, to help us to work with you to develop these products further. And I'll leave it at that. Thanks for listening.
We'll move to the questions, but thanks very much. Just one question, maybe for Dwi before we get going, are we seeing in numerical modelling in general that this coupling of AI with the, I guess, more traditionally physically based numerical modelling, is that a common thing now in the modelling community, or is that something that's still just emerging?
I think it's something is still emerging. One example is in weather forecast, where you may have some of the data-driven forecast from Google. They could get the forecast up to 11 days, if I remember correctly. But you can see that most of the weather service is still using physical by model mostly, and the reason it still need some time to actually overcome the reliable running that in a operational way using both only data driven or physical based. But I like to say that the exciting step that a lot of people are actually getting into now, where they try to couple hybrid. You have a lot of data, right? Historical data, and one way to deal with that is now, how could we actually couple that with all the process-based model to doing it a better forecast. So, but it's still emerging, and a lot of people already get in touch and working on it.
We've got a few early bird questions. I'll read these out, and if Dwi and Tim can answer them, that would be great. How can other researchers help to assist or partner in collecting in situ observations for calibration and validation?
So I can have a crack at answering that one. I think we're always interested in hearing from you and in having additional data sets to help with our water quality information across different water bodies in Australia. We are doing, colleagues are certainly doing a large exercise at the moment, which is collating water quality data across a number of variety of sources across different states. I think you can appreciate how difficult that is when things are in such disparate locations and very differently organised. And that's quite a challenging space, but all of that will help for us to validate our algorithms. We're very much interested in hearing from you and partnering. And I think also, one thing that is really useful to us is actually just thinking about, if you're doing in situ observations, timing your observations to the days that satellite overpasses are being undertaken. One of the things, of course, when we have what we call a matchup, where in situ observations have been taken at the same time and on the same day as the satellite overpasses, it essentially makes that comparison a more accurate one, and we can reduce errors our uncertainty. So one thing, Sentinel-2 satellites pass over every 5 days. It's quite frequent. So certainly one thing people can do is just adapting their sampling systems to actually to suit with satellite overpasses. The other areas are in reaching out and for us, looking at opportunities for us to deploy our instrumentations on other in situ sensor networks that you might be operating, I think is another nice way to really work together as well. I'll leave it at that, Richard.
Maybe
I
we
also
could.
sorry.
You go, Nguyen.
Oh, I also want to add that one part of the concept slide you see earlier. One thing is called eyes on water. And that is one part that is not only researcher, but all the community knowledge where normal people could actually use photo to take, use your phone to take a photo of the water body. And we use the Fourier scale to put that and process that in our model as well. So that is one part for collecting data as well. So there.
So what about some of these community groups like AquaWatch who are regularly going out, and would you like them to do the same thing? Would that make sense?
Yes, yeah, that's another really important, and that's another thing we colleagues have been working on. Colleague Janet Anstey in particular is a citizen science app, an adaptation of a European-derived app for Australian water conditions called Eye on Water, which uses the mobile phone camera to take pictures of the color of water, and we can convert this into a sort of normalized color scale of water, and we can essentially convert satellite images to exactly the same color scale. So it's a very good way of actually performing calibration and validation of our satellite images. So that is another aspect, certainly that we're working on as well in the citizen science space.
Then maybe what we can do is, separate to this, we'll just prepare an email out to people with just a bit of a guide of how they can assist in terms of with their field observations and how they can get hold of that app that Janet wants them to use. So maybe we can put a little information bulletin together if there isn't one already, and we'll circulate that out to the registrants of the webinar. All right, we better move on to question number 2. Has there been any research regarding algal blooms on smaller water bodies that are becoming more prevalent in newer states?
So I thought I might tackle this a little in line with the last question as well, which on river widths. When rivers get narrow, they also become small water bodies, I guess, as well. So the sorts of spatial resolutions we're dealing with, I guess the minimum of that from space currently with Sentinel-2 is around 10 meters. Landsat is about 30 meters, and of course that restricts the size of water body that you might be detecting blooms in. Having said that, there's been in terms of smaller water bodies right across Australia, also there are a significant number of farm dams, and of course they've been understudy, not so much from the water quality perspective, more latterly so, but certainly from their influence on hydrology across Australia as well. And so there's been quite a lot of work done using satellite remote sensing to map farm dams with quite a lot of success, both within CSIRO and other areas. In this area, I think the sort of higher resolution commercial satellites play a significant part, and I think here the best example is the sort of PlanetScope data, which have a much higher of the order of sort of 3 to 5 meters resolution, but they do come with the caveat that they are commercial data and come with a cost. But some states have negotiated contracts with some of those companies to actually get data sets over parts of Australia. There have certainly been some very nice studies which in the US which have looked at this data and its value in evaluating small water bodies, and I'm sure that would also apply for water bodies in newer states. In America, the nice set of studies by Perrin, I think was the surname of a study done in Arkansas, which really showed the real potential of these these commercial satellite sensors for monitoring small water bodies. I think in newer states, a lot of those issues revolve around just the design of those small water bodies, not always put in place with the possibility of algal blooms occurring in mind in some ways. So there's design features that perhaps can be around depth, inflows and outflows and things like that, riparian zones certainly to capture nutrients that can be used to control algal blooms in those bodies. And in terms of river widths, I think you saw in the maps I showed earlier that we could certainly see some retrievals in the Murray-Darling system, where the river widths are wide enough for Sentinel-2 to take perhaps something that is 3 pixels wide, so it gives us confidence of what we're seeing is actually water and not associated land features or adjacency effects. We can certainly determine in certain reaches of those rivers water quality information.
You mentioned before that you get a flyover once every 5 days. So, I mean, there's lots and lots of satellites up there. You're just referring to one particular.
Yes, I was referring to Sentinel-2. So which has a nice set of bands for monitoring, particularly monitoring chlorophyll concentrations. And there are 2 of them. They orbit every 10 days, but with the 2 of them in opposite orbits, we get acquisitions every 5 days.
And are they commercially available ones that have those same sensors on them? Or
similar, yeah. So the PlanetScope ones, and of course they are kind of what we might call small sats, and they have hundreds of them, of course, and so they're really designed to get daily coverage, but that comes with its own issues. Those daily observations are often made at quite different angles. So Sentinel-2 will always view a water body roughly at a similar kind of angle as it passes over. The planet constellation of satellites is really viewing from lots of different directions. That comes with its own issues. The spectral resolution of those devices is improving, as is their atmospheric correction, and their sort of intercalibration. They're getting much better at this.
on a slightly different thing, you mentioned, or Dwee did, about the use of mobile phone cameras for helping to ground truth this. Do you see AI coupled with just conventional cameras as being able to do more of this sort of work in the future? Take over maybe some of the hyperspectral?
Possibly, yeah. Only to a certain extent. I think that as you saw, some of the accuracy of those algorithms depend, and I'm only expressing my own opinion here, some of those algorithms depend on quite narrow spectral features in certain regions, and mobile phones can really only image in a sort of broad regions of the blue, green, and red parts of the spectrum. So there's a limit to perhaps what you can retrieve from in terms of something like a spectral feature or something like that. But there's a lot that can be done exploring that relationship between the images taken, say, with eye on water, which are of watercolor, and watercolor and water quality conditions. And certainly, I'm sure there's a lot, given time and resources, there's a lot that could be done on using machine learning, deep learning tools to tease that apart.
Yeah,
would be quite a fascinating study, actually.
Make a note. Number 3. Are there key warning indicators such as temperature or nutrient load, or is it usually triggered by a combination?
I could take it. So it normally is a combination. However, first of, I want to note that we're not addressing that in our model, because it is 1D, it depends on light and mixing, but it normally it's a combination between temperature, nutrient load, and mixing. So it both chemical and physical part. And for sure that they all depend on different species. However, for example, I could say a microcystis, and you would know whether it's an optimum growth temperature for that. It also have a lot of ratio of the nutrient between nitrate, phosphate, and niter, and all that kind of thing. And then whether it also break down of the stratification or mixing or not, and it carry out. And so to answer the question, yeah, it's triggered by a combination. It's hard to actually address in a complex model. And our model is more focused on the physical part, when you address temperature and light and mixing.
Okay. Question number 4. What width of river can satellites show chlorophyll A levels? Are you looking at biovolumes or VGA or presence, absence?
Well, I'll let Dewey answer the second component. Just moving on from what I was saying, I'll answer the first component and moving on from what I was saying earlier. For width or small water bodies or width of water bodies, we're really trying to view a water body that is at least three pixels wider than the satellite pixel. So if it's central zoo and 10-meter resolution, we're really looking at a 30-meter stretch of river, just so we reduce that level of uncertainty around whether or not the pixel itself is viewing part river, part adjoining terrestrial surfaces or shallow waters. So yeah, I would say it's really three times the size of the satellite pixel resolution you're dealing with.
3 times.
Yeah. To give us a level of confidence.
Volume of we also looking at the bio volume. So like I addressed earlier, we predict cell count, but it all depends on the number of species, how it's spread out in the whole water volume, the water column, and so we also want to address that. So the data normally we recorded not just cell count, but it also bio volume as well.
How dependent are you on like an in situ sensor, a fluorometer or whatever, to provide an indication of the algal counts of depth?
Yeah, so let's say that for example, the hydrospectra could give you an estimation on the surface. But if you could know what type of species is that, and then the type of mixing that you have, then you could also have an estimation of the concentration in the water column.
Presumably,
for sure that it still have uncertainty with it, but like I say that the more you bring it in, like if you know the mixing layer and you know the species, how the species react with that whole part of the buoyant mixing, then you could also answer the question of the concentration in the water column.
This is touching on the last question in the chat, actually, which is also about from Laurel.
Let's go to the chat then. Hold on.
Which is also about
keeping us moving, are you, Tim?
Mixed layer versus.
To get to the chat. Last time, fucking chat. Oh, it's down the bottom. Oops. Got the 2 screens going. Here we go. Well, we'll go in order, Tim. You'll just have to wait.
Okay.
First question from Dan Evans. How does the remote sensing technology overcome the surface area versus mass issue for TSS prediction? Therefore, lighter, more buoyant particles with larger surface area causing a disproportionately high return signal.
Yeah, this is a great question, and it's something that remote sensing probably at this stage doesn't do very well. So the concept here is that I guess particle size effect is how you might describe this, really, that finer particles, like silts that are suspended in the water, will have a much higher reflectance, say, compared to, and perhaps a higher than apparent total suspended sediment concentration, apparent, I say, compared to larger particles that then might have lower reflectance and therefore appear to have a lower total suspended solid. I think the only key thing we can do in this approach at the moment is and this is the example of the TSS algorithm that I presented here, is that we can do a kind of local calibration. So the relationship, the algorithm that we're using is one developed by Haneli Botha and Leo Limburner, and tailored to Australian waters. It was developed on that. But having said that, I would probably say that in many cases, and Dan probably knows more about this than I do, that different water bodies are quite unique in their behaviour of sediment and the sort of environment that they might be sitting in, whether they're a sort of mine waste, collecting sediment from mine waste or something like that, and other process. So they're quite unique. So I think the better the calibration you have for an individual water body, the better. So it tends to be site specific. That's what I was trying to say. But having said that, we're quite well placed to begin to understand some of those relationships, and certainly colleagues. I have other colleagues who've been very much thinking about this, not only in inland waters but also in the coastal domain. And we do try and actually couple our when we go out and make bio-optical characterizations of water bodies. We do take measurements around with absorption, with backscattering meters, also with particle size optical instruments as well. So we have actually a very good data set for inland waters, compiled job by Janet Anstey and colleagues over the years, which enables us to actually tease out some of these issues and derive more improved. And again, it might be something that machine learning can help considerably. I hope I'm not sure I've answered Dan's question, but yeah, there's a lot to it.
Decent crack at it.
And then
you see the same. Sorry, you see the same impact in phytoplankton. I should point out that larger phytoplankton contribute less to light absorption than smaller phytoplankton as well. That's called the package effect. So the same sort of principles apply.
Yeah. So I just try to talk about modeling perspective. So I'm just talking about literature here. I'm not doing it, but there's a model. It's called light climate model, where it actually try to resolve the spectrally with depth, where you get the absorption and then reflection of all particle in the water with different shape, and then the model split out the light coming out the water again. So yeah, maybe if we could do that with and then do the data assimilation with the data collection that we mentioned there, and I say couple with the hybrid modeling, then surely that the modeling could also help in this case.
Just a comment that we spend a lot of time trying to convert things to measures that we've conventionally used, like TSS, and we bust ourselves in half getting to a measurement that we've traditionally done because we could, evaporate off a sample and measure the suspended solids in it. Would it be more efficient just to say, hey, we've got this new way of measuring, we've got this satellite, and just use this machine thing to correlate, to come up with a new sort of parameter, like just out of, what do you think? Do you think that makes sense? Or are we busting ourselves because we've got all this other research data against those common parameters, and therefore we're wanting to correlate the two together?
And another feature is, though, that very often those existing water quality parameters are actually specified in legislation or in guidelines, and so organisations like water utilities and I guess state-based water quality monitoring organizations, very much play to the measurements of those parameters. So that drives, I think that drives a lot of, I don't want to call it resistance, but that drives a lot of that. Why we measure those things, because they're covered in guidelines, and perhaps if one thing, perhaps we're in that process of determining those guidelines, we're not fast enough to perhaps jump on what might be these new things that are coming in, like remote sensing methods, or even the egenomics, eDNA techniques and things like that. Yeah, it all takes time.
Yeah. It's interesting to reflect on. Okay, Yafei Zhu, that's the next question. How do you estimate the initial nutrient concentrations, e.g. nitrogen, and parameterize the effects of sediment geochemistry? Additionally, how do you parameterize the algal growth model?
Yeah, if let's say that the model that I'm using, the growth model I'm using, it's light and temperature dependent. We just say, assuming that it's limited nutrition, so there is no initial nutrition concentration that need to parameterize in just that model. It is surely a limitation. I'm sure that there is some model out there that taking care of this type of thing, but for sure that it will be more complicated in the processes. So it also depends on what type of the end user asking you. For example, the thing that we are trying to do is visit our a temperature forecast, mixing forecast, or certain type of blooming capturing forecast. So that kind of thing, that this model working well. We are not dealing with nutrient here. And how to parameterize the algal models. So I say that the input of that is meteorology, initial cell count, and all the physics, hydrodynamic input. That kind of thing, so that, let's say that we try to calibrate that with the in situ that we have, the cell count that we have. And then one thing that I proposed before, like say that, is it do the hypertuning thing with the machine that could also helping with doing the parameterization. I hope that answers the question, but if not, then my email there, the touch base later on after this.
All right, thank you. Julian Manning, what type of atmospheric correction was applied to the satellite imagery?
So I might be wrong, but I believe we're using, certainly in the coast for our coastal imagery, we're using the Acolyte algorithm, which is a algorithm developed by Quentin Belhallemont in Belgium, shown to be very good for sort of turbid water systems. I do believe we are using this in our inland waters. I'd have to really double check that though. So Acolyte was designed for aquatic, for deriving aquatic reflectance. So it's derived for calculating surface reflectance from water bodies, basically. Some other colleagues in CSIRO, Andrew Prata has done a very nice body of work using our Lucinda Jetty Coastal Observatory to validate that Acolyte procedure, and shows that it works really well. It's not the only atmospheric correction method we could use. There are quite a number of them, and over the years of AquaWatch, we have had quite a number of discussions around atmospheric correction, because it is a source of error, and I think we really just haven't had sufficient resources to really, it's a sort of topic you need a couple of postdocs to really sink their teeth into. We just haven't had those resources to undertake. So atmospheric correction is a work in progress, but pretty sure. I'm confident we do quite well with the Acolyte algorithm.
Next question is from Bozena Watchaziewicz. Great presentation, Tim and Dwee. My question is sort of following on one of Richard's questions. Could you please expand on the data types that are most critical for improving predictive accuracy of the AquaWatch modelling?
Okay, if that come up, like we have that XAI thing where we try to see that what type of data, what parameter will affect the most with the prediction. And then it just come up with kind of all sort of data and most of them it right now, like say that all physical parameter. So whether I say it about atmospheric meteorological data, or whether it go into the water data, water level, water flow, and all that kind of stuff. And so it hydrological, meteorological, and then it's still all physical. But in the future, because we try to do knowledge-based machine learning, so that while in the future we hope to also improve that with certain type of chemical and then ecological data as well, to show that it surely that will help with the prediction of AquaWatch modeling. Yeah. And I'm sure there's maybe some certain colleagues out there already trying doing that.
All right, we're 1 minute over. Laurel Fabro, what potential do you have RE water with a surface mixed layer of 3 meters but a hypolimnion much clearer with a benthic bloom developing, or is this something for the future? Oh, we might have stumped them on the last question.
No, well, I was thinking this. I thought this question followed on from what we were discussing earlier. Certainly, it's a limitation of hydrospectra. It sits above the water surface, so it's only measuring sort of algal concentrations, let's say, to sort of one optical depth, and that optical depth varies depending on what's in the water. One of the ways around this is of course, we can take profile measurements, and I think you were kind of referring to that, Dwee, earlier, to overcome these limitations where the algae are not sitting on the surface, but they're actually sitting deeper in the water column.
Yes.
Certainly there have been some methods, recently, which I'm really not on top of, that have been trying to look at the depth at which algae are sitting. There's been some nice work in the ocean color area on that. Yeah.
And what AquaWatch is doing, it's we're dealing with not the deep layer blooming that the model trying to address it, whether our surface bloom could actually carry out by mixing to the bottom, to down into the subsurface layer. And one thing is that, okay, we try to figure out what is the mixing depth, and then try to couple that with, okay, the measurement of margin error of doing that in a different depth. But again, deep layer phytoplankton bloom is something I don't think that we deal with that in AquaWatch yet. But I know certain place. I actually visit the LGB lab in Berlin last year, and they are dealing with a lot of that. So if Lara, could actually go and maybe do some reading on IGB lab, and they're doing with a lot of benthic blooming.
All right. Well, Tim and Dwee, we have come to an end of the questions, and just want to thank you both very much for presenting today. It's amazing the work you're doing. I'm very excited about that coupling of AI to numerical modelling. I think that's going to make a big difference, not just in your area of application. But thanks very much to both of you, and we'll send out a template of sorts, I guess, or a document just on how people out there can assist with providing their measurements, etc., or get involved more with the program.
Great. Thanks very much, everybody. Yeah. Great to present. Cheers. Thank you.
Thanks, guys. Bye for now.
Cheers, Richard.
Thanks,
Cheers,
everybody.
Dwee.
Thanks.